Okay, good morning, everyone. We're really happy you've joined us today for our webinar. Today's webinar is Irrigation Technology for Water Conservation with Dr. Michael Dukes. And if you feel so inclined, we'd love to hear, where you're from, and if you're with a company that you'd like to include, we'd love to have that information. You could type that in the chat box. And once again, we just want to welcome you to the Florida Friendly Landscaping Professional Webinar Series. So today's webinar is approved for one FNGLA, Florida Water Star, LIAF, DBPR, Landscape Architecture, and FDAC CEU. There is a $10 administration fee to receive the CEU, and I'll put a link for that in the chat box. And you can just make payment for the certificate if you want a CEU. After today's webinar. And if you don't mind, go ahead and if you do want that CEU, make the payment by the end of the day, because what we'll do is we will enter those CEUs to the licensing agency tomorrow to make sure everyone's had a chance to give us their information. This webinar is part of a monthly webinar series held on the second Tuesday of the month at 10 a.m. Our next webinar is From Landscape to Table with Dr. Norma Samuel. And you may have noticed your microphones have been muted, but please put any questions you have into the chat box and we'll take them at the end of today's presentation. Also, you'll see a survey invitation pop up, and please take a moment at the end of this webinar today to fill this out. It really helps us determine what educational programming that we offer and to make sure we're meeting your educational needs. So with that, I'll turn the screen over to Tom Wickman to introduce today's speaker.
Thank you so much, Claire. My name is Tom Wickman. I'm the statewide GIBMP coordinator, all with the Florida Friendly Landscaping Program, and it's my pleasure to be able to introduce our speaker, Dr. Michael Dukes. Dr. Dukes is an irrigation specialist focusing on the efficient use of water in irrigated systems. According to the U.S. Geological Service, Floridians used about 6.4 billion gallons of water a day in 2012. Due to the need for adequate water to produce food and satisfy domestic uses, including landscape irrigation, it's very important to maximize the efficient use of water. Dr. Dukes and his team are conducting research on high-tech irrigation controllers that apply water based on measurements from landscapes. These smart irrigation controllers are saving millions of gallons each year in Florida and are being adopted across the U.S. Dr. Dukes is also the director of the IFAS Center for Land Use Efficiency. This new center is taking an integrated approach to solving water and land use issues. The Center for Land Use Efficiency combines the Center for Landscape Conservation and Ecology faculty with the Program for Resource Efficient Communities and the Agricultural Best Management Practices programs. The Center for Land Use Efficiency, or CLU, was created to bring IFAS agricultural and urban BMP programs together. Dr. Dukes publishes in many journals and publications and is well known throughout the country. Today, his topic is irrigation technology for water conservation. Without further ado, let me turn the floor over to Dr. Dukes. Take it away.
Thanks, Tom. Thanks, Claire. Good morning, everyone. I see lots of familiar names. So welcome. Many of you have seen substantial portions of this presentation before, but let's get right into it, because as you will see, and as you know, this is an important topic. We are a growth state, and Florida 2070, or Florida Water 2070, predicts substantial growth in our state, and that's what you see here in these red areas from where we were in 2010 baseline, and then projected growth scenarios depending on what we do in the meantime. In any case, today we're around 21 million people. Water 2070 says by 2070 an additional 15 million people, and what this will do, this will essentially double the municipal water demand. And they go on to say that the single most effective strategy to reduce water demand is significantly reduce the amount of water used for landscape irrigation. And when they say that, I believe they mean potable water. So I'm going to start this story almost 20 years ago, or maybe 20 years ago now. Kind of lost 2 years during COVID, but approximately 20 years ago, when I came to Florida as a new faculty member, we were engaged with St. Johns River Water Management District almost from the day I arrived to start this project looking at single-family home irrigation in the Central Florida Ridge. And it turns out in that study, we documented that these homes were using around 70 inches of water per year. And that's in contrast to a maximum irrigation demand for these types of landscapes of less than 30 inches per year. Meanwhile, this is on top of a year average across that 2.5 years of around 50 inches per year. So roughly 120 inches of water input to these landscapes when they only needed around 30. And that red area you see there in the graphic is the difference between what was applied and what was estimated as the need for these landscapes. So by any measure, lots of over irrigation going on. And the reason we got involved is one of the developers the district was working with had their own consumptive use permit, and they were exceeding their permit. So let me switch gears a little bit. And I know a lot of you have seen this diagram. I like this diagram so much. I prefer to talk about irrigation efficiency rather than water conservation, although water conservation is a piece of that. But if I'm already a deficit irrigator, I already don't irrigate so much, then it's going to be hard for me as an individual to conserve water. So let's talk about efficiency, and we'll get into that, how that relates to conservation. If you imagine, this is how irrigation demand and how irrigation is modeled by our water management districts, by agencies and so forth, and by fellow scientists. Imagine the root zone of the plants. You have this air, plant, water, soil system. And so that's what's depicted in the top graph. You have plants growing out of there, and we're trying to irrigate such that we don't have runoff or water doesn't flow below the root zone. So that would be wasted water. So we're trying to satisfy the ET demands of these plants. Well, there's two components to irrigation efficiency. I think of them as the hardware and the software, not literally, but kind of conceptually. And the hardware is all the nuts and bolts. That's the sprinklers, the pipes, where you put the sprinklers, you put the right sprinkler in that has the right coverage, where the drip lines are, so on and so forth. And so if you have a problem in a system that's not very well designed, in other words, it doesn't have good coverage, or it's a system that is not maintained or then you have something that might occur that looks like the figure in the middle right. And that would be, you would see an under irrigated area. And this time of year is when we would see that in Florida. As we're greening up, the weather's getting warm, we don't typically have so much rainfall. And so you can see these signs in the landscape at that time. What we think happens, we don't know for sure, but what we think happens is a number of individuals managing their irrigation system, maybe homeowners, they would then overcompensate to meet the needs of that one spot, that deficit spot, and then that will cause over irrigation in the remainder of the landscape. And the problem of our unique conditions in Florida is that we do have well-drained soils for the most part, and you just do not see signs of over irrigation as easy as you would if you had heavier soils. So what problems do I speak of? We've seen them. We've all seen them. Here's an oldie but goodie. Impact sprinkler. We see this all the time. You probably, if you're out and about, you probably would see this at least once a day. Broken sprinklers. This is a maintenance issue. Maybe that head needs to be relocated to somewhere where it won't constantly get run over. And then there's just, I really don't know. This was taken by a former student of mine, Mary McCready, when she was an extension agent in Miami-Dade County. Yes, that's asphalt. Yes, they did go around the sprinkler. As a matter of fact, I was traveling about a week ago, and I was down in the Tampa Bay area, and I took a picture of a sprinkler, and they had poured the concrete around it. The sprinkler was in the concrete. So this is not a one-off thing. Anyway, let's go to management. Let's just presume that we have a system that is well designed and installed and it is maintained. Let's just presume that's the case. And there are a number of mechanisms how that is attempted to be achieved in the state of Florida through codes and standards. There's a voluntary irrigation licensure process. There's also local licensure for irrigation contractors. So all of those mechanisms are in an attempt to have better designed systems and in some cases maintain systems. But the next piece of irrigation efficiency is the management, and that is the when and the how much of irrigation occurs. So it's timing and how much. And you can have a perfect system as depicted here in the middle left, meaning it applies water evenly to the target zone. You're getting water to the plants. Everything looks good. It's roughly uniform application, meaning if your goal is to apply a ½ inch of water to an irrigation zone, it applies a ½ inch approximately everywhere in that zone. That's what I mean by uniform for sprinkler irrigation. Similarly, for drip irrigation, you would want to apply a similar amount to, at the first plant in a row, to the third, to the fourth, to the fifth, and so on. So this system is good, it's well maintained, but due to some type of issue with management, meaning when and how much to irrigate, there is over irrigation and water just drains through the profile. Like I said earlier, we don't see this a lot. It's just not visually apparent so much. It's easy for this to happen in our well-drained soils. And that's where, as Tom alluded to, the smart irrigation controllers come in. This is just a way I think about defining them. There are definitions that are out there, but essentially they measure some type of variable, or they're fed some type of information, whether it be weather or soil moisture, and then they utilize that information. So there's feedback. Right now, if you have an irrigation system and it just has a timer, that timer doesn't know what happens. It sends a signal. It doesn't even know the water's running if you don't have a flow meter connected to that timer, and most systems do not. So it's an open loop. And what the smart irrigation controllers do is attempt to close that loop partially by measuring some type of weather or variable in the irrigated area. And then they either schedule irrigation or they alter the schedule to meet those conditions. And you can imagine this time of year when it's starting to get warm, your landscape is greening up, you're going to need irrigation. And they would measure that. They would measure the warmer temperatures, or they would be fed an ET signal. And then in the winter, when you need less, they would also be fed information to accommodate that changing in the weather. Okay, so back to our story. 20-ish years ago when we did that project, at the time, there were no smart controllers, or they were in their infancy, and they were small startups, and they just really weren't commercialized at the time. So what we did, and what's been done for decades in agriculture, is we took historical weather data, that's rainfall and ET, or evapotranspiration, and we conducted basically a historical look at those data and estimated that the irrigation demand based on the ET taking water out and the rainfall putting water back in. And so we came up with an average schedule over time, and my graduate student at the time, went out to these homes and adjusted the time clock monthly. So we did see some gains, and you still see there's some red there. So there's some over irrigation. That's not, we didn't want to get too close to that theoretical demand, that bottom line, because in the real world, the irrigation systems aren't perfect and the coverage isn't perfect. But we did see substantial savings, 30% savings. We had a lot of room to save. So by just adjusting the time clock. And subsequent to that, we've altered our recommendations to adjusting the time clock really 4 times a year. You don't really need to adjust those time clocks monthly, because a lot of people just aren't going to be able to do that. That brings me to smart controllers. There's 2 types, soil moisture sensor controllers. You might hear me call these SMSs. That is a soil moisture sensor that is installed in the irrigated landscape, coupled with you can see over here on the lower left, what I call an interface device. So that's the brains of the smart controller, or of the soil moisture sensor controller. And that's coupled with or connected to a 24-volt AC timer. You can see there that's an older model timer, and they will work with any 24-volt AC timer. Here's a picture of both a timer and a soil moisture sensor interface. These happen to be the same brand, but they do not have to be the same brand in most cases with an add-on device. And the interface device simply regulates the signal that goes from the controller to the electric solenoid valves. I'll show you a diagram of that. So your typical timer, when it's the day and the time to irrigate, sends a signal to the valve opens, and you get irrigation. With a soil moisture sensor controller, the interface device is wired in between the controller and the valve. And relative to a set point, and in this example, it's 12%. Don't get hung up on the numbers. All the manufacturers have slightly different numbers and they mean slightly different things. It's really relative. So if the set point is 12%, that's the threshold. If the measured water content in the irrigated area is less than that set point, I can hear you. If I were in the room with you, I can hear you. You're telling me it's going to water. Yeah, it's going to irrigate. And that's exactly what happens. In contrast, during rainy weather, or let's just say that a previous irrigation event filled the soil profile adequately above the set point, so rain or irrigation, then the interface device is not going to allow that scheduled event in the timer to occur. So this is important because this type of technology does not turn the irrigation system on. It simply either bypasses or allows scheduled cycles. Okay. So calibration, probably the bucket method, what we call the bucket method, is the best way. Really, once the probe is installed, then you have to saturate it with water. It has to be really good and saturated. You have to fill the soil profile up with water around that sensor. The bucket's easy. You could run the irrigation system. I could imagine this would be convenient in certain cases, but in general, that's going to take a lot of water to run the whole irrigation system. Maybe that could occur during the time of landscape installation during the day. But in any case, I think the bucket method's probably more convenient in 90% of the cases. You saturate the probe with the bucket, and then most of the interface devices have a sequence of buttons that you press, and that tells the interface device that you are calibrating it. And what that does is if they do have this automated feature, what that does is it allows them to then start a countdown. So the soil is saturated with water, and then it allows the water to drain for 12 to 24 hours. So to get to that field capacity level, if you want the soil physics type of definition, and then the interface device will set the threshold, usually slightly lower than field capacity, to provide a little bit of buffer in there. And that's it, it's calibrated. Now, if water is added to that sensor during that calibration process, you have to start all over again. In other words, if it rains during the night when you're trying to do this calibration, then you have to start all over again. How about probe location? I will wait, I don't know, 5-10 seconds and ask you, is this a good location? You can type it in the chat, or you can keep your answer to yourself if you like. Of course, I'm preaching to the choir here, and the choir is answering no. Yes, I agree. No, yes, right. I agree. Not the greatest location. This actually doesn't look too bad during the time period I took the photograph. There is some sun there, but typically these areas where the houses come together, and I was just down with a builder last week looking at a lot of the new constructions two-story, because the lots have gotten smaller. And so you have even taller sides. And so these areas just don't get any sun. And often, not in this case, but often they're a swale. They're designed to be a swale for drainage, because the primary goal is not to have flooding in the houses. So these areas tend to stay wet, not the greatest location. This looks a lot better. Of course, you can't really tell from a photograph. You have to walk the site, but there's a full area of sun. There's healthy turf grass here. And we recommend that turf grass area is likely the location for the soil moisture sensor probe. By the way, let me take a step back. I'm implying that's a one sensor system. There are products out there that are multi-sensor systems, so you can have multiple sensors. So it's a sensor in each zone if you wish. Many of them are single sensor systems. And if that's the case, then you need to install that sensor in an area where the plant type will require irrigation the most frequent, and that's going to be turf grass. That doesn't mean it needs the most water. It just means it will dry out before your other plants in general. And then if you wanted to, you could, in the other zones, alter the run times so that those zones were getting less water when they did get irrigated. So in other words, if you had a shady area of ornamentals and the turf grass is deciding just when it's going to irrigate, then that runtime could be adjusted to compensate. The probe has to be in the root zone, basically. And for turf grass, we recommend 3 inches. There are, I have known contractors to install these a little bit deeper, maybe 5 inches, maybe 6 inches. The problem is the signal, the soil moisture signal looks like this. Imagine an up and a down. Up means water's being added, rainfall irrigation, down means ET. And that signal gets dampened the deeper in the soil you go, to the point where if you go below the root zone, essentially the only signal, you don't see the extraction of ET. You don't see the plants taking water out. You just see water being added, usually by big rain events deeper in the profile. So in the root zone, I have had contractors tell me they successfully have installed these 5 inches deep or so in other parts of the country because they aerate. So we don't typically do that here, but if that is a concern, it could be a little bit deeper. There are 4 brands here, and you can see they all look a little bit different. In general, the probe installation is once you find the site, then you're gonna dig a hole for the upper left and the lower right. And then we recommend installing that sensor in the undisturbed soil wall. So now you have actively healthy, good roots in good condition. You haven't just picked a big piece of sod and put the sensor on it. And then backfill the hole, put that piece of sod down. So that sensor is now in an area where there is really no damage to the roots. So it can get started immediately. The other 2 you see here, this one is a wireless, also shown here in the lower left. And then this one here is a granular matrix sensor. It's much smaller, so much less invasive. Those are, always follow manufacturer instructions, but those are much, well, not much. They're more straightforward. You don't have to dig a big hole. You kind of, a smaller hole, or for the wireless, you just insert it. So a little bit of research from the early 2000s. This was initial studies. Within this 2WOS is no sensor, so it's a time-based schedule with no sensor. It applied around 60 inches during the time period of the study. The 1, 2, and 7 day per week was something we were interested in to test how the sensors worked at different water restrictions, daily week water restrictions. Within each of those, there's 4 brands of sensors that we tested. And you can see the overall average is 72% savings. This was during rainy conditions in a well-controlled research plot area. So we were able to avert any problems. We were able to control as many variables as possible. So not the real world yet, but we're going to get there. Good results, 72% savings. And turfgrass quality was not impacted. Maybe you might have guessed that because of the rainy conditions. This is the actual site. There's 72 plots here, and you can see the figure there sort of shows you the square. It's square, but we're looking at an angle. Square plots, and of course dormant in the wintertime. The data I showed you were from the growing season. The next technology of smart controllers are ET controllers, which stands for evapotranspiration controllers. They are also called weather-based irrigation controllers by the EPA WaterSense program. And there's 2 general types. There's a signal-based and an on-site weather measurement. And it's been fun to watch the evolution of these over time, because in the early days, there was 1 or 2 manufacturers who were building signal-based, but at the time, if you think 20 years ago, we just didn't have the wireless technology that we have now, the cellular networks, this, that, and the other. And it was expensive. It was $5 a month to get the signal to the controller. It was a really good concept, but it was a little ahead of its time, in my opinion. And people just didn't want to, they either lost track or they didn't want to pay the $5 a month. And so that didn't really work so well. The technology worked well, but that whole signal part of it didn't work really well. And the other was on-site weather measurement. And that's where you have sensors that are coupled to the controller, and they measure some parameters in that irrigated area and then respond accordingly. Interestingly enough, the industry's gone the other way now. It's gone to more signal-based, and I'll talk about that in a minute. There's 2 basic ways that most of these controllers work, and some that are kind of in between. The first one is a soil moisture balance. Essentially what that controller is doing, it's measuring rainfall, or it's getting a rainfall signal. It's calculating ET, or it's getting an ET signal, and it's adding the water, and it knows how much it tells the system to irrigate. So it's adding the inputs, subtracting the outputs, and calculating soil moisture. That's essentially what it's doing. And then there's another one, the percentage adjust technique, I will say, or strategy. If you have a timer, you probably have a percentage adjust, and a lot of users like that because you can set it up for your 100% could be your maximum runtime, which in Florida is probably going to be May, dry, warm, higher ET. And then in the wintertime, you can dial it down to whatever percentage you wish, 50%, 30%, whatever that percentage is, and that automatically adjusts your runtimes. Well, this controller does that, but it does it based on some type of weather measurement to bring that schedule up and down. So you have to program in the runtime for the peak period. And the manufacturers do have guidance on that. All right, so inputs are very, very important for ET controllers. Here's just a few application rate of the zones. That's really, really important. The defaults are never right. For when I say a default, I mean, it may have a selection for spray heads and it says that's 2 inches per hour, rotors, 1/2 inch per hour, so on and so forth. It's best to measure that in the zone, and that can be done. That could be done with catch cans or some type of container throughout the zone, or I prefer using a water meter. So you get the exact gallons that go through that meter when that zone runs, and then you can compute. And we have methods to do that in our written documentation, how you can do that. They have selections for plant type, sometimes for microclimate, meaning sunny or shady. And then, as I said, the one type of controller, the percentage adjust, needs a base schedule for the region. And you could use really any schedule that's out there. We have them on our IFAS website where you can pick the schedule for the warmer period of the year, and then the controller goes with that. Weather data can be on-site or remote, as I said, and I think I've covered this. Schedule, the soil moisture balance calculates run times, whereas the percentage adjusts a base schedule. All right, these are just 3 examples, a photo that I had of them lined up from left to right. One, that's the Rainbird ESP SMTE, no longer available on the market. These things come and go depending on customer preference and so forth, and technological development. The middle is a Hunter solar sink, and by its name, you might guess one of the measurements it's using. It's measures solar radiation and temperature. The Rainbird measures rainfall with a tipping bucket rain gauge. I really like that for our localized rainfall conditions that we have in Florida. I really, really do like that. The solar sink has an expanding disk rain sensor, not as good. And the smart for on-site rainfall measurement, that is. And the Weathermatic Smart Line on the right measures temperature and rainfall with an expanding disk rain sensor. So the better you can measure rainfall, the closest to the irrigated area with these types of controllers, the better the controller is going to perform generally. Okay, well, this is back to the sprinkler coming out of the asphalt. This is not rocket surgery. It's really not. We see this all the time. You know, this is a high-tech system, and we've got the weather pack, the sensor package under palm trees. Better, this is much better. And sometimes people, they will criticize soil moisture sensor controllers. And I have to say that, well, if you don't put the sensor in the right spot, it's not going to work right. Well, I completely agree. But if you do this with an ET controller sensor package, you're going to have the same thing. So, you know, picking one or the other because of that is, I don't think, a really, really good justification. They both can have their place. One of the things that's happened in recent years, as we all know, we all carry around a pocket computer, and we have access to data that was unimaginable 2 decades ago. So there are these weather networks out there, Weather Underground, Weather Bug, National Weather Service. The data is everywhere. And what manufacturers have done is they've started to pull those data into their controllers. And that's a really popular technique now. So they don't have to worry about having a sensor on site that's put in the right spot. They don't have to worry about that sensor package failing over time. They're just getting this weather data feed. Some things you do have to worry about, though, is are the data you're getting representative of your site? I know there's a Weather Underground station near my house that it seems to never get rainfall. So I don't know. Another product out there that the National Weather Service has is this FRET, the Forecast Reference ET. Really, really neat. They use their forecast products, like they forecast, as we all know, they forecast temperature and all kinds of variables. And they run that through a number of algorithms, and they're forecasting ET. And what you see here, just as an example of, I'm in Gainesville. This is approximately Gainesville. Actually, it might be Marion County, but 0.16 inches of ET. This was in May of some year, 2020. That is, so that's starting to get up there for us. 0.2 and the low 0.2s is kind of the max we see. But look over here in Texas. 0.35, 0.33, 0.34. These are some of the highest ET numbers we have in the country. Pretty neat, but the product's available, it's freely available, and manufacturers can utilize that, and they are. Another component or development is apps and controllers. And this really lends itself well to the ET controllers. As a matter of fact, on the right-hand side, you see the ratio, and that is almost exclusively, or it is exclusively managed via the app. There's really no way to go into the controller on the panel. In contrast, the HydroWise to the left, you can program it via the controller or the app. The app's probably a lot easier because that's really where the manufacturers are pushing it. Offers a lot of convenience. Some of these have, like the HydroWise has a contractor mode where a contractor can buy a subscription, and then they can have access to all the programming that they did to that controller. So they can revert back if it gets messed up somehow. Pretty neat features. Okay, so in 2015, I did a summary with the sort of the question, do they save water? The answer was yes. But there was this big divergence between research studies, the 40 to 70% savings, you saw some of those numbers, to less than 10% real world. Well, why? It came down to implementation. In the early days, there were giveaways, and many of the controllers ended up getting in the hands of customers who were not really high irrigators. That's fine. Maybe they want the convenience of the controller. Maybe they want to optimize their water application. Maybe they want to put it on semi-autopilot. That's fine, but they weren't saving water because these weren't the high users. So sometime in the mid 2000s, I saw some folks on here from Orange County, so you can correct me or date me. Sometime in the mid 2000s, we started talking with Orange County Utilities about a smart control project. At that time, up to that time, we had done a number of research projects, but we really hadn't gone big in installing them on homes in a large utility area like OCU. So what they did at that time, OCU had about 130,000 single family home customers, and they gave us the data, the meter data, monthly potable meter data. These were all potable customers. And we analyzed that data over a 3-year period, and they had to have excess irrigation at least 3 months out of 3 years for every one of the 3 years. The idea is we were trying to target the excess users, because if the utility is going to implement a program, it's monetarily, it's more efficient for them to go to where the issue is, go to where the excess is, and spend money on that. That allowed us to identify 7,400 homes. You can see here the theoretical irrigation demand for that time for a kind of a standard landscape was about 3 inches per month. And we identified customers that were 1.5 times to 4 times that amount, because we were doing this on a high level. We had to make a lot of assumptions about the landscapes, about many different things. So we wanted to make sure they were excess users. And this is what the distribution of the homes looked like. The county sent out letters to all 7,400 homes asking them if they want to be part of this project. We got about 800 responses, and then whittled that down to probably over 300 site visits, and then whittled that down to about 169 participants in the end. And they were clustered into neighborhoods, and we had weather stations that measured representative rainfall in those neighborhoods. And the setup was 2 technologies, ET, that's the Rainbird ESP-SMT you see again, and then the baseline WaterTech S100 soil moisture sensor controller. So there were 2 groups there, as you see, and then those were further divided into a plus OPT group. And the plus OPT group was a group where we went back behind the contractor. We had one contractor do all the installs, and I think I see him on here actually, a good contractor, but we wanted to optimize our installs, the OPT installs, using the best practices we had developed over the years to see if that improved the performance of these devices. All these homes had a water restriction exemption, so they could water 7 days a week. And that was one of the questions, because during that time period, we heard a lot of people saying that these should be allowed to water 7 days a week. We didn't necessarily think that was the case. So the OPT, one example of difference, OPT had a 3-day water window per week. That doesn't mean they watered 3 days. That means they had a water window of 3 days per week where they could water. In the case of soil moisture sensors, I've seen those not water for 2 months at a time in the summertime. when we're getting plenty of rain. And then we had a comparison group that didn't get any technology. Every one of these homes got an irrigation meter. And we proceeded with the study. Fast forward through 5 years. I'm going to close out with this. The comparison homes are on the left. You can see how much water they are applying there. And then the different treatments go to your right with ET plus OPT, SMS plus OPT. We had 2 different soil types in the county that we wanted to look at. Generally the flatwood soils or the historically poor drain soils, they had more organic matter, held more water. They required less irrigation. And we saw that signal even in the comparison homes. But if you compare, here's the percentage savings from 11 to 41%. Let's look at the OPT. So OPT saved more water on sand soils for the ET controllers, but there was no difference on the flatwood soils, no significant difference. Whereas for the soil moisture sensors, the flatwood soils, OPT saved more water, but no difference on the sand soils. So sort of mixed results, but the way I kind of think about it is the plus OPT was never higher. So it has the potential to be lower, but it was never higher. So we still recommend those best practices in terms of installation and programming. We think there could be some benefit, at least based on these data, about half the time. So in 2020, I went back to the literature because at that time, in 2015, a lot of the work honestly was coming out of Florida. Our water management districts funded a lot of work. So a lot of what we knew about these controllers was coming out of Florida. And the question was, well, does it work in other places? It's very different in the Carolinas and California and so forth. So since that time, there've been a number of studies, and I did another summary of those studies. And so we had studies from North Carolina, Kansas, New Mexico, I believe California. Then they showed 51% savings in research studies, and then in practical application, 30% savings. So that tells me that there's the organizations that are implementing these on a wider scale are doing a better job of targeting where they should go and installing them properly. There were some cases of negative savings, meaning a smart controller used more water, and that can be attributed to improperly set up controllers or putting an ET controller on a deficit irrigating property. ET controllers are designed to irrigate to the plant water needs. If your historical irrigation is not meeting the plant water needs, it's likely the ET controller, without tweaking, will increase your irrigation. Soil moisture sensor, remember, only bypasses what's in the timer. So if you don't mess with the timer, it will not increase your irrigation, only decrease. With that, I can take questions. I think my former technician, Michael Gutierrez, is on here. Thank you for the photos, Michael. I think this one's yours too.
Michael, thank you so much. One of the questions out there is there a limit as to how far a soil moisture sensor can be away from the controller?
The manufacturers do have limits, and it depends on that particular manufacturer. We're talking, 100+ feet for a wired sensor. And for the wireless, it's generally line of sight. So you got to be a little more careful. You probably aren't going to have good results if its receiver is on the other side of the house. So.
Okay. Are the wireless sensors pretty available at this point in time?
Oh yeah. Yeah. 100% available. I mentioned brands. We don't favor any brand. We like to test all the brands, but the only wireless one that's commercially available that I'm aware of is the Toro. It's a Toro Precision Series. There are some other smaller manufacturers, and I don't know the names off the top of my head, but I have seen them like at the irrigation show that offer wireless soil moisture sensors as well.
Okay. I see a question came in from Art. What does an ET number of 0.16 mean using FRET?
Yeah, that's reference ET is sort of a standardized measurement or kind of an index of how much water plants need. And that means 0.16 inches of water per day. That's how much the plants transpire. Actually, you modify, let me go back on that. That's an index, and then you modify that based on the plant. So for example, if it's full sun turf grass, it might approach the 0.16. If it is turf grass in a partially shaded area, it could be half of that or 2/3 of that.
Okay. Do pressure regulators add to savings?
Yeah, Julia, I thought of that as I was putting this together. I think maybe next time I need to add in some more technologies, but yeah, pressure regulation, 100% save water. By the way, I didn't mention this too much, but if you go to if you Google EPA WaterSense, you can go there and find controllers that have labels. That means they've been independently tested and verified that they save water. We've done a lot of the test development for EPA WaterSense for both ET and soil moisture sensor controllers. But there's another technology, and that's pressure regulation, as Julie points out. Pressure regulating spray heads are another technology that's labeled by the EPA WaterSense program.
Great. Do you see benefits for homes versus commercial? Are you seeing, more benefit in commercial applications versus home applications?
It kind of depends on, I'd say the potential is there, but it sort of depends on the commercial application. Are we talking about a 200-acre business park, or are we talking about Bojangles that's in a strip mall? The smaller, what I think of as light commercial, that all these controllers would be applicable because they're probably running timers right now. But if you go to the large institutional and commercial parks, you're going to have options to buy ET and soil moisture sensor controllers, but they're different. They're much more expansive. They're 2-wire. They're more expensive, but they have a lot more capabilities to manage that type of irrigation system.
Great. You mentioned an irrigation show. Do you know when and where that was?
Google Irrigation Association. I believe next year it's going to be in the first week of December in Las Vegas. It moves around every year. This past year it was in San Diego. And of course, for 2 years, we didn't have it.
Great. Can you talk about the cost differences between the different systems you've mentioned?
I have seen ET controllers out there and soil moisture sensor controllers out there for less than $100. They're going to be more than, if you're trying to get something that's very, very inexpensive, they're going to be more expensive than a very simple controller, but they've come way down. They used to be, $500 to get in the game, but now you're looking at maybe $200 for a really well-known name brand.
Does the lifespan of the different sensors differ much, between something like an ET controller stuff versus soil moisture sensors?
We don't actually test for that. What we do know is the warranties on these, and I think the soil moisture sensors have at least the Rainbird has a 5-year warranty. If someone from Rainbird's on, correct me if I'm wrong, it's 3 or 5-year warranty. They will last longer than that. Also, the baseline will last longer. They'll all last longer than that. The only issue is the wireless one. The batteries are probably every couple years. You're going to have to replace those. As far as the ET controllers, the expanding disc rain sensor, if that's the technology they use for rain, that requires pretty frequent maintenance. We've documented that elsewhere. You'd want to replace those discs probably at least once a year. Other sensors on those, I would say at least 3 years. The manufacturers know these are going to be out there, so they're designing products that are robust and are going to last a number of years.
Great. Do you advocate the use of a master valve in an irrigation system for isolation purposes?
Sure. If you want to go crazy, master valve, flow metering, the flow metering would really, and with a smart control, would really bring, and that's Art there, so he knows I'm preaching to the choir again, but that would really close the loop on the control system. So the controller would know, for example, if you had flow that was too high, then it knows there's a leak and it's going to shut down. Usually those controllers have a feature where they'll shut down and they'll send you an error message. Or if the flow is not high enough, that's where you would get back to the master valve. So all those are great.
Super. Dr. Dews, can you discuss the sustainability of spray versus drip? Spray water loss versus drip having lots of additional material required in the landscape.
I'm not sure about that question. sustainability. I'm not sure exactly what that means. I will say that I'll answer it like this though. You know, we know as the water pressures are getting higher and higher, or the pressure on the resources is getting higher and higher in Florida and elsewhere, you know, drip has been utilized, sometimes required in areas that it makes sense, like landscape beds, because it can be set up to use less water. But it goes back to that irrigation efficiency piece of it. If it's done right, it can be more efficient, but I've seen it done wrong so many times. And the issue that I see in the practical application of drip irrigation, it's not maintained. It's put in and then it's just, you know, just not maintained. So it gets cut and then now you have a leak for the next 3 years that no one pays attention to. So that piece has got to be, I don't know, that's got to be part of the picture. Whereas spray heads, you can see the issue, you know, visually, so it's easier for that. And spray heads, they can be efficient. Generally, they're not as efficient as drip, but they can be efficient.
Great. Do you have to adjust the depth of soil moisture sensors over time based on root establishment or, you know, the plant material that's there?
I would say no. You know, like I said, I was with a builder last week and they were showing us how they installed the soil moisture sensors. They did that before the landscape was even put in, because the irrigation's installed and then the landscape goes in. Sometimes it's the same day, sometimes it may be a day or two later. So they had a technique where they were putting the sensor in at a given depth and then the roots would get to the sensor essentially. So in the early days, well, early on in a new landscape, you're going to have establishment irrigation anyway, but you know, they had a technique to compensate for that.
Super. It looks like you've gotten through all the questions. You know, you covered a lot of material and made it really understandable. Thank you so much. That was excellent. I see one more question come in. Can you mention what brand of SMS builders are currently using?
Well, I wouldn't say builders. I know this one builder that I visited last week, they're using the Rainbird Smarty. They're I think pretty much everything Rainbird, so that works for them.
Super. Well, Dr. Dukes, thank you so much. I see a question came in, you know, how can they see this presentation again? This will get posted to our website, so you'll be share it with your friends. You can make sure that other folks can you know, are able to see it. You can go back and watch it again if you want to, you know, you want to remember something that Dr. Duke said. You can always go back and watch it again. And so it'll take us you know, maybe a week or so to get it posted to the website, but it will certainly be available. And then just a reminder, on April 12th, again, we have Dr. Norma Samuel talking about from landscape to table. Dr. Dukes, thank you so much for taking the time this morning and sharing this knowledge with us.
Thank you. And thanks everybody. Y'all have a good day.
Everybody have a great month.